Welcome to the first lesson of Unit 1. Here, we will derive the fundamental equations of chemical equilibrium, starting from just the first and second laws of thermodynamics. Equilibrium refers to changes which may occur in a system. We say that we are in equilibrium when no further changes occur in the system, like in the two red and blue materials in the figure. In reality, that no further changes occur at equilibrium is only true at macroscopic level. At the molecular scale, there will always be changes happening. For example, molecules of components that move across the different phases, such as the liquids and the gas at equilibrium. However, while out of equilibrium, the motion of molecules happens massively and dominantly in one direction, for example, from the liquids into the gas phase. At equilibrium, there is no preferential direction for molecular motion. Therefore, molecular transfer in one direction are statistically compensated by transfers in the other direction. What we see at macroscopic level is no further changes in the system, a condition that we call equilibrium. A state of equilibrium is therefore defined in terms of changes in the system that are not macroscopically visible at equilibrium. What changes are we referring to? In principle, that's any possible change, such as those associated with transfer of heat, mass, or other forms of energy across phase boundaries. Thus, flow of heat and associated heating or cooling, expansion of or contraction of the system that we refer to as displacement of phase boundaries, or flow of mass away or into the system or across parts of it, such as across different phases. All of these are diagnostic of known equilibrium. Conversely, when equilibrium is achieved, none of those macroscopic changes occur in the system. When is such a special condition of equilibrium achieved? Mass and energy flow as a response of differences in some quantity. For example, heat flows as a response to a difference in temperature. Phase boundaries are displaced as a result of a difference in pressure or force per unit surface on the two sides of the interface which is being displaced. We call a potential the quantity that the differences of which cause the flow of mass or energy. The potential for heat flow is temperature, and thermal equilibrium requires that the thermal potential, represented by temperature, be the same across all phase boundaries. Similarly, mechanical equilibrium is achieved when the mechanical potential, represented by pressure, is the same across all phase boundaries. What is the chemical potential? That is, the quantity that should be the same across all phase boundaries in order to stop any further flow of mass. Well, we call this chemical potential the chemical potential. We do not have a special name for it, such as temperature for the thermal potential or pressure for the mechanical potential. For the chemical potential governing chemical equilibrium, our predecessors have been less creative and have referred to it as simply the chemical potential, usually indicated with the Greek letter mu. In summary, for a system made of different phases to be at equilibrium, we need that the pressure in all phases, the temperature in all phases, and the chemical potential in all phases be the same. However, for the chemical potential, things are a bit more complex. In fact, we are dealing with mixtures, meaning that there are many different components making up each phase. For example, a silicate is made of a lot of oxygen, substantial amounts of silicium, aluminum, and several other elements that we used to represent as oxides, such as silica, iron oxides, magnesium oxides, water, carbon dioxide, and so on. Each one of such individual components can move from one phase to another. Therefore, the principle that the chemical potential must be the same in all phases translates into a quality of the chemical potential of each component in all phases. Accordingly, this is how we write the general equilibrium equations. Here you see them for a system made of pi phases, indicated at the exponents, such as the liquid phase, the gas phase, and the number of solid phases represented by different crystal species. Equilibrium is achieved when pressure and temperature are the same for all phases, and the chemical potential of all components, here represented with numbers and subscripts in all phases, is also the same. For example, for a silicate melt to be in equilibrium with a gas phase made of components water and carbon dioxide, the requirement for equilibrium is that the temperature and pressure of the liquid and the gas phase be the same, that the chemical potential of water in the liquid phase be the same as that of water in the gas phase, and similarly, that the chemical potential of carbon dioxide in the liquid phase be the same as that of carbon dioxide in the gas phase. So we have now defined the general equilibrium equations. But are we satisfied with that? Or in other words, are we ready to apply the theory to real cases? Definitely not. In order to do so, we need to know how to determine the chemical potential for the components involved in chemical equilibrium. And to do so, we need to know more about chemical potentials. What are they, and what's the physics behind them? In particular, how do they relate to the first and the second laws of thermodynamics that I anticipate they entirely govern chemical equilibrium? This is what we are up to see. From here on, we abandon for a while chemical potential, but I guarantee that when we will be back to them, you will be surprised of how naturally chemical potentials emerge and how easy it is to understand their central role in chemical equilibrium. Here are the first and the second laws of thermodynamics. In their amazingly beautiful simplicity, they embed all of the physics and the equations that we will see developing throughout this entire training module. The first law tells us that there is a quantity characterizing any system that we call internal energy, which varies in response of flows of heat in and out of the system, and in response of the work done by or on the system. If energy is added or subtracted to the system in the form of heat, the internal energy of the system increases or decreases correspondingly. If energy is subtracted or added to the system in the form of work done by the system on the environment or work done by the environment on the system, the internal energy of the system also decreases or increases accordingly. In the simplest possible words, the energy of a system increases if other energy is added to the system, and it decreases if part of it is spent by the system. That's all we need to know of the first law of thermodynamics. What does the second law tell us? It tells us that there is a quantity called entropy, which, for an isolated system, that is, a system left to spontaneous evolution, cannot decrease. It can only increase if the processes that occur are irreversible or remain constant if the processes are reversible. Let's try to understand this a bit better. An isolated system is one that does not exchange neither mass nor energy, thermal or mechanical, with the surroundings. By definition, it is a system left to spontaneous evolution, because any external action would connect the system with the surroundings, therefore making the system itself not anymore isolated. Any spontaneous process is irreversible because for a process to approach irreversible conditions, we need to exert a strong control on the process itself in order to make it evolve very slowly and close to equilibrium. That would, again, make the system connected with the surroundings, such as ourselves controlling the process, therefore non-isolated. As an example, if we leave a gas phase free to expand inside the room, its expansion is an irreversible process. The second law tells us that such a process is associated with an increase in the entropy of the system formed by the gas and the room. The above is at the core of the concept of equilibrium. Any system evolves spontaneously in search of an equilibrium condition. What does equilibrium mean? It means, by the second law of thermodynamics, entropy maximization. When the entropy is maximized, spontaneous evolution ceases and equilibrium is achieved. That also gives us a direction of time. In spontaneous processes, that is, processes taking place in isolated systems, system entropy can only increase with time. That means that by simply measuring the entropy of two different states of an isolated system, we can establish which one came before. In other words, entropy gives a direction to time. Besides the second law of thermodynamics, there is no other known physical law that embeds the concept of time. For that reason, the concept of entropy has been referred to in the literature as the arrow of time. Let's now write again the first and second laws of thermodynamics. We can combine them by substituting the differential of the heat flow, dq, from the second law into the first law. And we can use a general expression for the work associated with phase boundary displacement, obtaining a relation which is of fundamental importance in thermodynamics. This is a combination of the first and second laws of thermodynamics. It tells us that the change of internal energy for a system that exchanges thermal and mechanical energy with the surroundings can be expressed in terms of changes of its entropy and volume, again with the equality sign applying to reversible processes and the inequality to irreversible processes. In other words, the state variable internal energy is a function of two other state variables, entropy and volume. Accordingly, if a process occurs at constant entropy and volume, then the right term in the fundamental equation becomes zero, meaning that in such a case, the change in internal energy of a system is zero if the process is reversible, and it is negative if the process is irreversible. Let's consider it once again. We are saying that any spontaneous or irreversible process that evolves at constant entropy and volume will continue for as long as the internal energy of the system decreases. When no further decrease of the internal energy is possible, then the process stops. That is, therefore, a criterion for assessing the equilibrium condition of a system. Let's minimize its internal energy while keeping constant its volume and entropy, and the condition of minimum internal energy will give us the condition of equilibrium. That's great, and it sounds pretty much like the criterion for equilibrium that we are looking for. But there is a limitation. In fact, such a criterion only works for processes occurring at constant entropy and volume. We can deal with such processes, but what about any other process? For example, processes that take place every day around us and that are definitely not evolving at constant entropy and volume. Fortunately, we can handle them as well. Legendre transformations allow us to work out the fundamental thermodynamic equation and define a number of additional quantities similar to internal energy, allowing the thermodynamic description of the equilibrium conditions closer to our experience. Simply stated, Legendre transformations allow us to switch between conjugate pairs of variables, such as pressure and volume, or temperature and entropy, by application of the product rule. Let y be a function of x, where x is an array of independent variables, such as volume and entropy, if y is taken to correspond to internal energy. Then we can define a new function z, as specified by the operator on the upper right corner, and we can apply that to each of the independent variables x. Let's see it in detail. Here, the fundamental expression for the internal energy is for simplicity reported for a reversible process, therefore with the equality sign. The internal energy is a function of the two variables, entropy and volume. Thus, x can be either entropy or volume. Let's say that x is entropy and apply the Legendre transformation. The new function z will be the old function u, internal energy, minus entropy, times the partial derivative of the internal energy with respect to entropy. We see from the fundamental equation that the partial derivative of the internal energy with respect to entropy is temperature. Therefore, we obtain a new function z equal to u minus st. We call this new quantity the Helmholtz energy, usually identified with the letter F. Here is an exercise for you. You can either try to solve it or skip it and continue with the presentation. It's totally up to you to decide how deep into the equations you want to dive. If just watching how they unfold or trying to obtain them yourself. In both cases, you will see the solution in the following. The exercise is this one. Use the Legendre transformations to see what comes out if instead of entropy, x is selected to be the volume. Then use the various forms of energy that you come up with and continue to apply the Legendre transformations to determine all of the energy forms that derive from the first and second laws of thermodynamics. Press pause now if you want to do the exercise. Okay, let's continue and repeat it by taking the independent variable x now equal to volume instead of entropy. By applying the same operator given by the Legendre transformation, we obtain a new function h equal to u plus pv that we call enthalpy. The same procedure can now be applied to the new functions that we have found, for example, to enthalpy. We start by writing the differential of enthalpy, and we find that it is still a function of two variables, this time entropy and pressure. So we can apply the Legendre transformations as we have seen above. Let's take x equal to entropy and apply the Legendre transformation. We obtain a new function g equal to enthalpy minus temperature times entropy that we call the Gibbs energy. And sometimes this is also called the Gibbs free energy. We can apply the Legendre transformation several times to each of the new functions that we have found, by continuing to change the independent variables. If we do that, we end up with the same quantities already defined here: internal energy, Helmholtz energy, enthalpy, and Gibbs energy. Each of these quantities is a measure of the energy of the system, and each of them is a state variable. Therefore, we can refer to each of them in our problem of finding a criterion for chemical equilibrium. However, while in principle they all do the same job in describing the energy of a system, in practice they are of different utility. The reason is shown here. In this slide, I summarize what we have seen till now. On top, we have the internal energy, that the combination of the first and the second laws of thermodynamics tell us to be a function of entropy and volume. We have then switched variables through Legendre transformations and have defined other three measures of the energy of the system, namely enthalpy, Helmholtz energy, and Gibbs energy. We can differentiate them and see how our attempt of switching variables through the Legendre transformations was indeed successful. In fact, enthalpy turns out to be a function of entropy and pressure. The Helmholtz energy is a function of temperature and volume, and this is the relevant part of the story, the Gibbs energy is a function of pressure and temperature. Let's summarize it once again. The second law of thermodynamics provides the direction towards which a system evolves, that is, the direction towards equilibrium. That direction is the one that maximizes system entropy. We have then combined the two laws of thermodynamics and have found another criterion for chemical equilibrium in terms of internal energy. For a process evolving at constant volume and entropy, chemical equilibrium is achieved when the internal energy is minimized. That's fine, but not ideal, as we do not commonly refer to processes that evolve at constant entropy and volume. Legendre transformations give us other quantities describing the energy of a system, which are a function of different pairs of independent variables. Because they all derive from the combination of the two laws of thermodynamics, they all lead to a criterion for equilibrium, each one referred to processes developing while different pairs of independent variables are kept constant, and each one ultimately corresponding to maximization of system entropy. Among them, Gibbs energy is particularly convenient, just because it refers to processes that occur at constant pressure and temperature, and that corresponds to our experience. It is the usual way we approach physical problems and perform experiments in the lab. We used to think at processes which occurs at a given pressure and temperature. And in that case, when we refer to a given pressure and temperature, it will be minimization of the Gibbs energy, which provides the criterion for equilibrium. Well, we have started from the first and second laws of thermodynamics and have derived not one, but a series of equilibrium criteria, each one appropriate for processes evolving under different conditions. But don't forget where we started from. We want to understand what is the chemical potential and why it is so central for chemical equilibrium. Now, it's time to go back to it and discover the connections between chemical potential and the various energy forms that we have derived and that are reported in this slide. This will be the contents of lesson number 2. See you there.